All right, thank you, Reynold. Now that we discussed how to get your data into the lakehouse, let's put it to work. In this talk, we'll focus on data science and machine learning workloads, which are key to driving business value. But of course, it often sounds easier than it is. Data don't always come in perfect form, you don't always have a fully staffed up team, and insights don't just jump out at you. In reality, there's an entire lifecycle of exploratory data analysis and transformation before you can even begin. A tongue-in-cheek way of summarizing this is that data science is mostly about data cleaning and equal parts about complaining about data cleaning and actual data science. Now that we're finally done with data analysis and transformation, we can turn our attention to what we came here for, data science and machine learning. But as you know, that's not as easy either. Machine learning itself is also an iterative process that requires a lot more than just hitting run on a notebook. Models need to be trained, tuned, and experiments should ideally be reproducible. Many publications agree that the vast majority of AI projects fail before they even reach deployment. Now, of course, there are many solutions that address these problems. However, we're still not done yet. Once you arrive at a model that looks like it may work, there's still the small matter of actually putting it into production, safely and reliably. This is what is commonly referred to as MLOps. Here's an example of what that looks like in the real world. 3 weeks to develop a model and almost a year to deploy it. Now, why is that so hard? Well, it's because of isolated teams, a wide variety of open source tools that keep changing rapidly, and the fact that models don't often behave the same way in real life as they did during experimentation. Taking all of this together, it is clear that data science and machine learning is quite an undertaking that requires a team to work together. But it is hampered by 3 big problems. The hardest part of data science is still data. Experimentation is complex and needs to be reproducible. And putting ML models into production is prohibitively difficult. But what if one platform could support the entire data science lifecycle? Well, that's where we come in. Databricks helps make data teams more productive by providing a collaborative workspace, an environment that facilitates experimentation and makes it reproducible, and infrastructure that accelerates the delivery of data applications to production. Together, these are the attributes of a complete platform for the full data science and machine learning lifecycle. So let's take a closer look at what's inside the box, starting with our workspace. The first thing you want to simplify is compute management. No one really wants to care about how their compute and environments are managed. So we provide one-click deployment of optimized runtimes, but also the flexibility to customize them. For machine learning workloads specifically, we pre-install the most popular machine learning libraries like TensorFlow or scikit-learn and make the use of GPUs turnkey. With compute ready to go, we provide a unique collaborative notebook environment that supports multiple languages and cloud-native features like co-presence, co-editing, and commenting, just like you used to from Google Docs. To take notebooks to production, we recently introduced support for arbitrary files, so that you can factor your notebooks into libraries, store your environment specification alongside your code, and automate your workloads. Finally, we believe in choice. And we have a large user base that prefers using RStudio, PyCharm, Jupyter, VS Code, or any of the other popular editors. So we currently provide a managed version of RStudio and plugins to connect to Databricks from your tool of choice. With our exploratory data analysis and data preparation done, let's move on to experimentation. Connecting data to machine learning models requires several domain-specific capabilities that are part of a feature store. Feature stores are a central place to manage the lifecycle of inputs to machine learning models, so-called features, and make them available for training and serving models. A lot of time and energy goes into engineering these features, and they are often valuable in terms of intellectual property. So we want to make sure to facilitate well-governed reuse of these features by making them discoverable in a central place. And through the integration with MLflow, we also significantly simplify the model deployment process. The feature store makes sure that features are available consistently for training and serving, and MLflow models can automatically look up features from the feature store, even for low latency online serving. Now that we're finally starting to experiment with machine learning, we found that true experiment tracking and reproducibility only works if it requires zero work from your data scientists. So we automatically capture metrics, parameters, model artifacts, code and cluster configuration, library versions, and even data versions if you're using Delta Lake. And this gives you all of the benefits of reproducibility with none of the extra effort. Now, once models are trained, they become assets whose life cycles needs to be managed. Our model registry has truly become the GitHub for machine learning, and some of our customers manage millions of models with it. To facilitate MLOps, we've added access controls that manage who can release models to production, webhooks to integrate with CI/CD systems, comments, email notifications, and much more. Importantly, this model registry is agnostic to the machine learning frameworks you use. You can even package up arbitrary code and store them as MLflow models. Now, with our models in the model registry, we're ready to move on to production. But of course, besides data and models, there's also code that needs managing. With our new repository-level Git integration, we make sure that all members of a data team can follow best practices by performing Git operations through the UI. Admins and DevOps engineers can use APIs to set up automation with their favorite CI/CD tools. And we support any type of Git deployments, even if they're in private networks. Once you have a versioned workload you want to automate, our new multitask workflow management feature allows you to orchestrate any type of workload from ETL to machine learning. This capability is native to Databricks, but we also continue to support integrations with popular third-party orchestrators like Airflow. And finally, there are a wide variety of ways you would want to deploy your machine learning models. Because we leverage the MLflow model format, we support any and all modalities of model deployment, from large-scale online serving to on-device. That being said, we have streamlined the two most common paths. One click to deploy a model as a batch job to a large amount of data, and one click to deploy a model as a REST endpoint on an auto-scaling cluster. This new capability gives you production-grade serving at your fingertips. So now that we've covered most of the elements of the data science lifecycle, let's take a look at it in action in the Databricks environment.
Welcome to Databricks. The Lakehouse is a simple and open data platform for storing and managing all of your data that supports all of your analytics and AI use cases. It's where data scientists and data engineers and analysts collaborate to prepare and analyze data, build models, and deploy them to production. Today, we will focus on the data scientists who, as you will see here, are trying to explain life expectancy from health indicator data. And along the way, we will see how our platform supports the whole life cycle from data ingest to production. The notebook-based environment you see here is Databricks. You can edit, run, and share code and documentation and visualizations and output in many languages. We will look at the problem in three parts: data access and preparation, modeling and interpretation, and finally, deployment. We're going to only briefly review the work of the data engineer in Databricks here. Her goal is to make raw data usable. This includes fixing errors in the input, or standardizing representations and joining disparate data to produce tables ready for use by modelers and analysts. Here, the input are just CSV files from the World Health Organization and World Bank, and an additional drug overdose data set that we included to explore as a factor. And they can be read directly as is, from distributed storage as Spark data frames. Note that these data sources could just as easily have been a SQL database, or JSON files, or Parquet files, and so on. The schema is automatically read, or inferred in the case of CSV. These files contain about 2,000 different health and demographic features for 16 developed countries over the last several decades. The goal will be to learn how these features predict life expectancy, and which one or two are most important. So, the data engineers might prefer to work in SQL and Scala, as here. Databricks supports these in addition to Python and R, which the data scientists might prefer. All may be used even within one notebook. And along the way, Even the data engineers can query the data with SQL and see the results with built-in visualizations, like this one. They might want to take an early look at the data, and we see that clearly the trend in life expectancy between 2000 and 2016 looks different for the USA. It's low and declining, and the question will be why. So at the end of the data engineering workflow, the 3 data sources are joined on country and year and written as a registered Delta Lake table. So to the data scientist, this representation doesn't make much direct difference. It's just a table that can be read like any other data source. But Delta Lake provides transactional rights and lets the data engineers update and fix data from a bad feed or gracefully modify the schema or enforce certain constraints on the data, and that does matter to the data scientists. Anyone who's faced modeling on dumps of data from a database that might break or change in subtle or silent ways will appreciate the real data science problems that these factors can cause downstream, and that Delta Lake helps fix. Or, for example, consider the need to recall exactly what data was used to produce a model for governance or reproducibility. Managing the data as a Delta Lake table allows the data scientist to query the data as of a previous point in time. And this helps with reproducibility, of course. Note that everyone can collaborate on this notebook, perhaps leaving comments, like this one. So here we pick up from the world of the data scientist. Her goal is to explore the data, further enrich and refine it for this specific analysis here, and produce another table of featurized data from modeling and production deployment. So the collaboration began simply. Read this table of data that the data engineers produced. This notebook uses Python, and the ecosystem may be more familiar and useful for data science. The Spark API is the same, and the data tables are available in exactly the same way, however. Now, you don't have to use just Spark and Databricks only. For example, here we dropped into Pandas to fill in some missing values before returning to Spark. You can define efficient UDFs, or user-defined functions, for Spark that leverage Pandas too. The Python ecosystem offers libraries for visualization too, and with Databricks, likewise, you can just use these. Common libraries like matplotlib and Seaborn are already built into the ML runtime, and others can be added easily. Here, the data scientist uses Seaborn to generate a pair plot of a few of the features such as life expectancy, literacy rate, and opioid deaths per capita. It can highlight correlations such as that between per capita expenditure on healthcare and GDP, and it also reveals a clear outlier. So the outlier here with respect to opioid deaths is going to turn out to be the United States again. After some additional featurization, the data is written as another Delta Lake table. Now, the dataset is small enough that it's possible to manipulate and model with tools like XGBoost and Pandas, all of which are available already in the runtime. But Spark will still be relevant in a moment. The data scientist is here developing modeling code using XGBoost. It will regress life expectancy as a function of the 1,000 or so features left in the input. But building a model really means building hundreds of them in order to discover the optimal settings of the model's hyperparameters. Typically, a data scientist might perform a grid or random search over these values and wait hours while the platform crunches through each of them serially. Databricks, however, provides a Bayesian optimization framework called HyperOpt in its runtime, which is one modern and efficient way to perform the search in parallel among others. So given a search space, HyperOpt runs variations on the model in parallel across a cluster, learning as it goes which settings to give increasingly better results. HyperOpt can run these variations in parallel using Spark, even though the simple modeling here doesn't need Spark itself. This parallelism can dramatically lower the wall clock time that these hyperparameter searches take. The results are automatically tracked using MLflow and Databricks. This gives a quick view of the modeling runs that were created in this notebook, and we can drill into the experiment view. This is the MLflow tracking server, and this experiment shows a more detailed overview of these trials. We can use this to search through runs and even compare them as here. For example, we might want to compare all the runs using a parallel coordinate plot, and in this way figure out which of the combinations of hyperparameters seem to produce the best loss. This detail view also shows, for example, who created the model and with what revision of the notebook, when it was created, and all the details of the hyperparameters including loss. It also includes the model itself, along with feature importance plots that the data scientist created. The model can now be registered with the Model Registry as the current staging candidate model for further analysis. The Model Registry is one centralized repository of logical models that are being managed by Databricks. It manages artifacts and versions of this model, and manages their promotion through staging to production. This particular model has a few versions registered as versions of the same logical model, and they can exist in states like staging and production. The Model Registry is also accessible in the left navigation bar. Instead of managing models, as for example, a list of coefficients written down in some file or a pickle file stored on a shared drive, the Model Registry puts a more formal workflow around tracking not just the artifacts of the model, but which ones are ready for which stage of production deployment. So next, a manager might review the model and the plots. Here's a feature importance plot created by Shap, and it shows that the feature that most influences predicted life expectancy is mortality from cancer, diabetes, and heart disease. Low mortality, in blue, indicates higher life expectancy and appears to explain +1 to maybe -1.5 years of life expectancy. And year is next most important, which unsurprisingly captures many of the cumulative effects of better health over time. So notice that drug-related deaths do not appear to be a top explanatory feature overall. Other diseases still dominate. So after reviewing the model and other plots, the manager might finally approve this model for production. The deployment engineer takes over here. She loads the latest production model from the Model Registry, the one that has been approved for deployment, but MLflow automatically converts it, if desired, to a Spark UDF, or user-defined function. This means it can be applied to featureize data at scale with Spark with just one line of code. Now, this could work equally well in a batch scoring job or with a streaming job as well. So, for a second, compare this to, for example, handling the model or even just the coefficients to a software engineer to attempt to correctly re-implement as code that could be run in production. Here, the exact model that the data scientist created is made available to production engineers, and nothing is lost in translation. So in this production job, for example, the data is applied to inputs from 2017 to 2018, for which life expectancy figures are not known. And this can be joined with data up to 2016 to complete the plot we saw earlier, showing the extrapolated trends. Now notice that this could be registered not only as a UDF in Python, but also in SQL as well. So note that the predictions appear fairly flat, but this is mostly because over half the feature data is missing in later years. And this model could also have been deployed as a REST API or as a service in Amazon SageMaker or Azure ML. So this has been a simple example of how Databricks can power the whole lifecycle, from data engineering through to data science and modeling, and finally the MLOps tasks like model management and deployment.
Before we close out this presentation, there's one more thing that I wanted to share with you. Many of the steps I showed you in this lifecycle require fairly technical skills, but we believe that data-driven decisions shouldn't be limited to a few. So we decided to make significant investment to broaden the audience of Databricks. Maybe you've already seen some of the coverage. We acquired a company called 8080 Labs that built a no-code solution for data analysis and preparation. The goal was to find out if we can have our cake and eat it too. Can a tool for citizen data science actually have real-world impact? And as it turns out, we have already proven that with our own AutoML product. It provides a UI workflow that actually generates native Python code in the background that can then be integrated into production systems. Bamboolib, the product built by 8080 Labs, turns out to have the exact same attributes and perfectly complements our AutoML product with functionality for data analysis, preparation, and transformation. Here's a quick example of how visual data transformations actually generate code, in this case pandas. And to be honest, even experienced data scientists would have probably had to search on Google to find out how to do these transformations. So together, we showed that you can indeed have your cake and eat it too, with citizen data science done right. So in summary, Databricks provides a complete solution for the entire data science and machine learning workflow, from data analysis to production. You can find many resources online on how to get started. Just follow the short link on this slide. And with this, I'm going to hand it off to David, who's going to talk about what's next for Databricks.